Welcome back, everyone. In this video, I'll be going over the lecture for the linear approximation section. Now, what the linear approximation and an idea in the second half called the differential are, they're just going to be ideas of using the tangent line for something. In the past, we've calculated equation of tangent lines. We figured out when the tangent line would be horizontal. And the main reason we practice that is it's an important idea to understand what the tangent line looks like. So probably the most important thing that I talked about is that tangent lines lie very close to the actual graph when you zoom in. All right, so I'm going to highlight that. Tangent lines lie very close to the actual graph when you zoom in closely to a point. Now we've seen graphs before, but I want to go ahead and just graph an example for you. And I already have this one made up. It's the graph of y equals x squared, and the tangent line is at the point 2, 4. You can verify that this is the tangent line equation because I have the x and y value here, x1 and y1, and then the slope. If you figure out the slope here, do the derivative and plug in 2, you get the 4. So the point is, right here, Desmos does a really good job of a lot of things, and one of the things it does is it will tell you where the tangent line hits the graph as long as you come up with the correct equation. But if we zoom in, the tangent line equation, which is the blue one, once again, keep finding my point here. The closer we zoom in, we notice that we basically can't even see the red line because it's directly underneath. And if I switch to the red one by clicking it, then we can't see the blue line. And we've seen this before, but the idea is you zoom in closer and closer, you'll pretty much get to the point where you only see the one that's on top. At this point, we can barely see any blue right here. If we do the blue one on top, we can barely see any red. But the idea is this closeness. What we want to do in this section is understand that you can use the tangent line to approximate things and find possible errors of things, which is very important. And the reason why the tangent line is used is because it's just a line. It's just a linear equation. If we solve this for y, it would just be y equals mx plus b, and that's really the easiest kind of equation to work with. So what we're going to be doing in this section, we'll start off. We know how to figure out the equation of a tangent line. What we're going to do is just rewrite it in a way that makes sense, as far as instead of writing y equals, we'll use a function name. And then we'll kind of work with that a little bit, see how we can use it to approximate things. And then in this back half of the section, we'll use the similar related idea called differentials to actually estimate errors of things. All right, so I pretty much went over this, but the new terminology here is that when we use the tangent line in a way to approximate values, which is what we're going to be doing in this section, we use the term linear approximation. When you're talking about linear approximation, you do have to understand what function you're looking at. So we'll be looking at f of x for this one because in the formula below here I have f and f prime, and we're going to be approximating it at x equals a, and we can point that out because of the a's here. We have a, and a. Now what I want to go ahead and do is just help you realize very quickly that this is just the tangent line equation that we have been dealing with before using point slope form. And I'm just going to do this very quickly. So in general, we have y minus y1 equals m times x minus x1. This was our equation of a line using point slope form. Well, we know the derivative is the slope. So since we're talking about it at x equals a, m is f prime of a. X and y are our variables. Those don't really get anything, and that should be y1. And then y1, well, that was the value we got by plugging in the x1 value. The x1 value was the value we were given in the problem, so this would be a. A is x1. And then y, because we have a function name, it would be f of x1, which is f of a. Well, now all you have to do to realize this is the same equation is if you add the f of a to each side, you get y equals, and typically with linear approximations, they put the f of a in front. You can write it in back if you want, but I'm just going to match the formula here. F of a plus f prime of a times x minus a. And all we did from there is, because this is an equation of a function, instead of writing just y, we want to realize it as something more significant. They rewrote it as L of x. And like I highlighted above, it's got a main name, which is linear approximation, but it's also could be called the linearization. So both of these names pretty much mean figure out the tangent line of your function at some point. So to practice this, we'll just have two quick questions. First one here, it says find the linear approximation of the function g of x equals the cube root of 1 plus x at a equals 0. Then use it to approximate the cube root of 1.1. Well, what we want to do here is realize that this first part, let's not worry about the approximating part. What is this first part here saying? We want to approximate or find the linear approximation specifically, because there are other ones, but we only know about linear approximation. We want to approximate this function at this a value. Now you can memorize this formula, which would be fine. But if you also realize it's just the equation of the tangent line, that might help you memorize it, or you could just think about it finding the tangent line of this at this x1 value of 0. It doesn't matter which way you think about it. I'm going to use the formula just because we just derived it, so we know it's the same one. But if you want to start with the equation of a tangent line using point slope form, figuring out the derivative, which we're going to have to do anyway, by all means. Right. But the main thing that you're going to do here is that we need a, which we have. You have to be given a in your formula. And we could very easily figure out f of a, or in this case, g of a, because we would just plug in 0. So let's go ahead and do that. G of 0, which is like our f of a here, because we're using f instead of g, or g instead of f. We just plug in 0 to our function. We got the cube root of 1 plus 0, and that's the cube root of 1, and the root of any root of 1 is always 1. So f of a, or g of a, which we're going to use here, is 1. Now the other thing we need is g prime of 0, because we need the derivative, and then we have to plug in 0. Right, so that means we've got to figure out the derivative of this thing, g prime of x. Let's go ahead and do that. Let's do it on the left or the right here. G prime of x. Well, if we go ahead and rewrite g of x, because it is a radical, it's best to rewrite it as an exponent. G of x is the same as 1 plus x to the 1/3. Cube root is the same thing as the 1/3 power. We should be comfortable with that. And then the derivative says, well, let's do the power rule with the chain rule, because the inside's not just x, but we start with the power rule, bring the 1/3 down, rewrite the inside, 1 plus x, subtract 1 from the power. 1/3 minus 1 is negative 2/3. And then we multiply by the derivative of the inside. Well, the derivative of 1 plus x is just 1. So you can visually write 1, or just realize that the derivative of the inside is 1, and you don't even really need to write it. But one thing you should do is, because we're actually going to be evaluating and plugging in x equals 0, it's probably better just to go ahead and get rid of the negative exponent. So that's the only thing I'm going to do here. On the top, we had the 1, and since this is all going to the bottom, the top is just 1. The bottom of our fraction, we have a 3 already. And this 1 plus x is going to the bottom, and the exponent becomes the positive 2/3. So this is our derivative. Now we want to plug in 0 here. Let's go ahead and do that. G prime of 0, we would get 1 over 3 times 1 plus 0 to the 2/3. 1 plus 0 is 1, which makes this 1 over 3 times 1 to the 2/3, and any 1 to any power is just 1. So this is 1/3. You could probably notice here that if we were plugging in anything or besides 0 here, it'd be really messy, and we'd have to use a calculator anyway, which almost defeats the purpose of linearization. All right, so we've got g of 0, we got g prime of 0. That basically means, as far as our equation goes, we're done, right? Because now we want L of x, we want the linearization. Actually, I'm going to go ahead and start by writing it right below there. L of x. Before I plug in, I'm going to turn this formula for linearization into the one specifically for us. We have the letter G instead of F, so everywhere you see F, put G. and we're doing it at a equals 0. So the first part is g of 0 plus, next part, g prime of 0 times parentheses x minus 0. Right? And you'll notice now that I've actually plugged in, you can believe that we found the two things we needed to. We have g of 0, which is 1, plus g prime of 0, which is 1/3, times x minus 0. Well, that's just x, so I don't have to write the parentheses anymore. And we've got our linearization. That's the main part. But just so you can see how it could be used, we want to approximate the cube root of 1.1. How are we going to approximate this? Well, you have to keep in mind what your function is. Our function is the cube root of 1 plus x, and we want the cube root of 1.1. So the cube root of 1.1, what we're trying to figure out, if we think about it in terms of our function, we have the cube root of 1 plus 0.1. Right? We would get the cube root of 1.1 if we plugged in 0.1 in for x here. Well, the idea is the linear approximation tells you this is basically equal because 1.1 is close to 1, where we started. Or you can kind of think about it as the 0.1, what we're plugging in is close to 0. But what our linearization is telling us is the cube root of 1.1, which is this, g of x, is basically equal to L of 0.1, right? Because this is our x. And now what we do is we go ahead and we plug in 0.1 for x in our linearization equation. Notice that our linearization equation is very small, and it's going to be easy to plug in 0.1. So we have 1 plus 1/3 times 0.1. Now you can do this all by hand. This one you don't need a calculator at all. We have 1 plus 0.1 is 1/10, so this would be 1/30. And if you want to get a common denominator here, this would be 30/30, so 30 plus 1 is 31/30. Now this may not be very meaningful, so at this point, yeah, you'd probably have to type it in a calculator just to get some decimal, because at the end of the day, we are trying to approximate a cube root. And, you know, if we don't really have a number there, it's sort of unsatisfying. So let's just type in what is 31/30. And let's just say we want to round it to 4 spots. Well, you can see it's just 1.0 and then 3 repeating forever. So 1.0333 would be our answer. Now, if you wanted the exact approximation, which kind of is contradictory because approximation is exactly what it sounds like, you're not getting the exact value, but you could stop here. If you want to get it to some decimal points, plug it in. But one thing we might as well go ahead and do is see what is the cube root of 1.1. Well, if you want to type that in a calculator, the easiest thing to do it is just realize that the cube root is the 1/3 power, so 1.1 raised to the 1/3. We are a little off, but you can see we're not that far off. The cube root of 1.1 is rounded to 4 spots, 1.0323. So we're off by the third decimal spot. We're off by 0.001 or 1/1000th. So we're barely off. And the nice thing is, if you're really good and comfortable with fractions, you actually could have figured this out by hand, but there's no reason to do that because we have the technology. Right, so that's the main idea with linear approximations. We can use it in other ways, but the main way it's used is to find errors using the differentials, which are going to be in the second half of the section. Now, what I wanted to do is just do one more that I think is kind of fun, and it's just one that is pretty common to find a linearization of because its linearization is so simple. And it says, find the linearization of the function f of theta equals sine of theta at theta equals 0. We don't want to do anything with it. We could use it to approximate sine of very small angles since it has to be close to 0. But I just want you to see the power of linearization. So for this one, we'll probably go ahead and, instead of using x, use theta just to match our variable. The linearization of this function, well, just following our formula, if you want to write it down, until you get used to it. That's okay. We would have f of a, which is 0. So we have f of 0 plus f prime of 0 times theta minus 0. So just using theta instead of x. Now keep in mind that this can be written as theta equals 0 or a equals 0. It's understood that this is really representing a equals 0. So just the clarification here, this one says a equals 0, which makes it easier to draw parallels to our formula. But when you're finding a linearization or a linear approximation, when you're told to find it at some point, a is just a letter to represent, but you can still use the original variable theta. All right, so we can see here, just like last time, we need the function evaluated at a, and we need its derivative evaluated at a, which is 0. So what is f of 0? Well, we plug in 0, we get sine of 0, and sine of 0, hopefully you remember, is 0. We also need f prime of 0, and since the derivative of sine of theta is so easy, you might be comfortable just doing this in one quick step, but let's just go ahead and write down what is f prime of theta. What is the derivative of sine of theta? That is cosine of theta. And remember, it's positive because it doesn't start with a c. But that means f prime of 0, we just plug in 0 to cosine now. We get cosine of 0 equals 1. Now, the great thing about this linearization is you'll see something so simple when you plug it in. It's, I don't know, I just think it's pretty cool. We get L of theta equals f of 0 is 0 plus f prime of 0 is 1 times theta. Just to emphasize, we're plugging it in. Even though I've already had 0 written there, I'll write minus 0. But what does this simplify to? Well, this 0 is gone, so this is really just 1 theta or theta, and then we're adding 0 to it, which means it's just theta. Well, what this is saying is that if you want to figure out sine of small values by hand, this is just a little side note, sine of theta, if theta is close to 0, well, what it is, it's very close to theta. And I'll just throw in a value here. Now, theta being small, remember you're in radians, so you have to be careful. A small angle in degrees would be like 1 degree. But in radians, if you do 1 radian, that's a very large degree. That's about 60 degrees. So that's not a good idea. But if you did like sine of 0.1 radians, you don't, as we've never done, and I won't do anymore, just to emphasize though, when you pick small values, you're almost always going to be in the decimals, and usually you might even go 2 decimals, meaning you'd have 0.0 something. But what this is saying is sine of 0.1 is about 0.1. And we can just go ahead and just use the calculator, see, is this actually true? What is sine of 0.1 about? Well, you can see it's pretty much 0.1, because if I asked you to round just to 1 spot, you get 0.1. If I asked you to round to 2 spots, you'd even get 0.10. But the idea is as you get further and further away from 0, it's not going to be that great. So like I mentioned before, if you have sine of 1, that's a kind of a big angle of 60 degrees. And we saw that it's not very close, 0.84. 0.84 is really not close to 1. That's when it gets kind of big. But if you're asked to use or approximate sine of 0.1 or 0.05, you can see it's pretty much 0.05. But the idea of being close is relative. So 0.3 is this close to 0.3 itself? I mean, it's pretty close, but depending on your problem, it might not be good enough. My general rule of thumb is to say that if you're within 0.1, that's the farthest away I would go. That's the farthest away I would make A. You'll notice that, or X rather. You'll notice that in the first example, we actually did use X equals 0.1. We just weren't asked it directly. And this one, I wasn't asked to do anything. I just wanted to show you that this works. but I use 0.1 for a reason. I didn't want to go beyond that because that would be a very large number, relatively speaking. All right, but that's a good place to stop for the first half. The second half is on differentials, and I'll see you there.